Today we have two talks. The first will be by Andrea Caputo from Tel Aviv University, who will tell us about Axions, dark photons, and radio data.
Exactly.
And next, we will have Joshua Foster from MIT, who will tell us about Axions from strings. So Andrea, the blackboard is all yours.
Okay. So first of all, thanks a lot for the possibility to talk. This is the first Blackboard talk that I do after 2 years. I'm Andrea Caputo. For people who don't know me, I'm a postdoc in Tel Aviv University with Tomer Bolansky and Michael Geller. And today I will be talking about something that I find very interesting and that I didn't know about, but really fits the topic of this workshop, that is physics from the sky. In particular, I'm talking about what is called the arcade excess, okay? That I didn't know about this excess. So arcade is a balloon that is measuring radio emission, the radio temperature in a frequency range between 3 and 90 gigahertz in something like 6-7 frequency channels, okay? And they put out some result in 2009, okay? The interesting thing about this is that they see something much, much above the background that you would expect from CMB in the antenna temperature, okay? So if you do a plot of this type, which there is here the antenna temperature as a function of the frequency, and here the frequency, then if it is just a black body, right, you will expect some constant value at the CMB temperature, like 2.72 Kelvin or something like that, okay? While arcade, that is working at frequencies that are much below Cobian Firas, okay, is measuring an excess. So here is arcade. And the actual interesting thing is that there have been a lot of other experiments also in the past measuring frequency lower than this, down to the 10 megahertz or so, and they all measure a very huge radio background, okay? So actually this plot looks like this, okay? And so everything is very well fit by something of this type. So T nu is equal the CMB temperature plus some correction that follow a power law of this type. Okay, where the spectral index alpha is something like minus 2.62, okay? And this TR is something like 1.19 Kelvin. And just to give you an idea of what, more particle physics friendly, that the temperature, the antenna temperature is connected to the number density of photons per unit frequency by this usual formula, right? So this is the formula that you should remember. And given that the spectral index is minus 2.62, okay, this means that here the dn over d omega, okay, will go like roughly 1 over omega to the 3 alpha, okay, 1.62 minus 1.62, okay. Remember this number because this will be our goal for our model in order to explain this excess, okay. Of course, one thing that I forgot, just interrupt me, no? I want this to be like very interactive, being a Blackboard talk. So if you don't understand anything, something like just ask me. Sorry? Is not thermal. So typically when you have this kind of, power law, you think about synchronous emission, right? Sorry, Sim? The temperature, you read from here, right? So TR is the temperature of this addition to the CMB, right? And this is like the overall scale for the intensity, let's say, but it scales with the power law. So typically, astrophysically, you don't think about thermal stuff. You think about like synchronous emission, right? Okay, this actually like we measure synchronous emission everywhere in our universe, a different frequency and in different location, right? What is synchronous emission is just you have charged particle, energetic, accelerated in a magnetic field, okay? So this will be something like dE over dt for synchronous radiation will be something proportional to Thomson cross-section, charged particle, right? Then you will have the magnetic field energy density, so proportional to B square, right? And then the energy of the particle, the Lorentz gamma factor. Then you have a bunch of them, a bunch of this particle accelerating in the B field. And typically you can produce radiation of this type with an index alpha that depends on the spectrum of the particles, okay? And of course, astrophysicists and astronomers are smart guys, so they try to explain this excess with synchrotron radiation, okay? The first, and this excess, like, you know, is standing there for many, many years. People tried different explanation for this excess. First of all, what I showed you is after subtracting the galactic contribution, okay? First thing that astrophysicists thought was, okay, maybe we didn't do a good job with the galactic contribution. So maybe, is this like from our galaxy, this excess? And the reason seems to be no, okay? And there are two reasons for this. First, X-ray observation. Okay, you may wonder why. Remember that the synchrotron radiation as a part that it depends on the energy density in the B field. We know that in our galaxy from Faraday rotation, the B field cannot be so large, right? It's at the level of the microgauss. So in order to fit that huge spectrum, the leptons should be very energetic, the charged particle. If they are very energetic, the inverse Compton scatter in the CMB, and they would produce a huge X-ray background that we don't observe. Second of all, this will also make our galaxy very peculiar among like the spiral galaxy, okay? Because basically you would need some very bright halo around our galaxy, and this is not something that we observe in all the other spiral galaxies, okay? So astrophysicists really think that all this is extragalactic, okay? So this signal is coming from extragalactic sources. So the answer here is yes, but also in this case, there are actually problems. Okay, there are in particular, there is one big problem. The number of sources that you would need is very, very large number of dim sources. So that is to say, sources that we cannot, resolve with actual experiments, but will be like much, much larger than the number of galaxies that we observe right now in the universe. Okay, so typically you expect to be like just 10% of 20% coming from this kind of very like dim sources. And second of all, you also would violate the relationship that we observe between the infrared and the radio emission in galaxy. Okay, the physical reason for this is that especially if you have star-forming galaxies, you will have radio emission because like you ionize the gas, so the electron will be decelerated in the ion electric field and emitting radio, okay? And also you emit infrared emission because of, for example, Lyman alpha that are get shifted and just stellar surface emission, okay? And there is a strong correlation between that. So if that background to galaxy, basically you would expect a much larger background also in infrared, and we don't see that, okay? So also extragalactic emission seems to be challenging for astrophysicists. And so people, particle physicists started also to think about other explanation. Yes, of course.
There is this paper that was written. There is this paper that was written a few years ago by Linden and Fang about cluster mergers. Have you seen that?
Yeah, so the cluster merger is one of the possibilities. So Tim actually worked a lot of this. I have to say that none of his like work, so they are all very nice work, but a lot of them like fails to explain different peculiarity of this signal. One of them I will explain to you like in a moment is due to homogeneity. Okay, so for example, that is one explanation. One of the best explanation by Tim is actually Alphen waves, so turbulent magnetic field. But even in that case, the fit to the data is not amazing. So you can explain very low frequency, but then you don't explain the larger one. At the moment, the best astrophysical explanation is supermassive black hole. So people claim that there are like population of 3 stars, very massive. So we are talking about then at the end 10 to a 6 solar masses for the black hole that you form. Okay, information is a kind of supernova-like event, so you produce very energetic particle, and then that will cause synchronous radiation. But also that is speculation, because you also need to have them in the redshift, and so every astrophysical explanation, and this is the best one, is also speculation. So people started to speculate about dark matter explanation, for example. Yeah, sure. Yes, sorry, I will. The CM, that's a very good question. It is actually related also to the second part of my talk in some sense. The Cobb-Virus measurement has but a couple of order of magnitude larger than this. Okay, so actually this is an important point. Like, and this was one of the explanations, for example, of models for the ages anomaly. If you heard about that, Cobb-Virus, all the measurement that we have for CMB are at much larger frequency than this by Arcade, couple of order. Okay, so you're not constraining by that, but by this other experiment.
But then, if the peak is on the right, why the temperature is not increasing?
No. Then here you will have this dashed line. You always have the CMB contribution, right? Then at some point.
So maybe I didn't understand well what was this temperature. It's not related to the intensity of the CMB?
The antenna temperature, whatever you see with your telescope. Okay, with for example, the Arcade will be just a part of the sky. With the LLSFF will be a full sky map. Is the number of photons that you receive in your frequency bin. Okay, and your frequency bin is different than the frequency bin virus that observe a perfect black body. If you would observe a black body, then the temperature would be the same at all frequency, right? That is the point, right? While instead they see like a different temperature, a different number of photons in different frequency channels they have.
So it's a deviation with respect to the black body.
Exactly.
Okay.
A lot of sigma.
Okay, thanks.
So people thought about dark matter, this is why I'm here and why I'm here in this workshop. Let's see actually time. Okay. So one of the first idea that was put out about dark matter was by my friend and collaborator, Marco Taoso, Marco Regis from Turin University. And this is just, you have some WIMP annihilating into leptons. And then in ordinary galactic field, then you can create some synchrotron radiation. Okay. And this is a cool idea, but it seems also that even in this case, the fit is not amazing. And actually is another problem. It's also for explanation like the one that Mina was mentioning about clusters, is that it's not only that this signal is actually very intense, it's actually also very smooth. So if you look at the fluctuation of this signal, they are actually very small. So the signal is very isotropic. That is to say, if you go and measure fluctuation of delta t over t, they are around like 10 to the minus 2 at multiple of 10 to the 4. Okay, so between like 10 and 100 like seconds. Okay, and so this is actually very difficult to explain, because if you have any explanation of dark matter that is coming in contribution is coming at low redshift, then they will correlate with structures, right? And then you would mess up with this observation, right? A very simple idea how to get that. Like if you work with CMB, all this kind of stuff, you want to compute in Fourier space, the multiple, this will be an integral over the comoving distance of your source that I call F and the matter power spectrum. Okay. So whatever is giving you the excess should come from redshift like larger than 5, more or less. Otherwise, you're not consistent with observation. So this creates a lot of challenges, and yeah. For this, yeah, because like if you plot the matter power spectrum, right? Of course, like at the the larger you go in redshift, the larger is the homogeneity in the universe, right? It's homogeneous. But then when you go low, then the power spectrum is changing, and so you will see structures on these scales that would be then imprinted in your signal, right? While when you do a plot of the CL as a function of the multiple of your signal, okay, you see a very small CL, okay, at the multiple that you can look at, okay. There is a caveat of this: the frequency, the actual measurement there are just like 10 and 9 gigahertz. But actually, this week there was another measurement at 550 megahertz, And also that measurement confirmed that the signal is very homogeneous, and the astrophysical explanation for dim sources is challenging, okay? And it doesn't seem to work very well. So this is why, with Maxim Pospalov, Josh Ruderman, and two amazing postdocs, Ongwan Liu and Siddharth Mishra Sharma, we decided to give our 2 cents. And so now I will explain to you our model for this success. Okay, the model is actually a very simple one. Is to say there is an axion-like particle A with some mass ma that is coupling to a dark photon. I will call the dark photon gamma prime, okay, and the normal photon gamma, okay. So then will be something like this, where the prime indicates the dark photon. And then you also have a part of the Lagrangian that is the relationship between the photon and the dark photon. And this Lagrangian will contain, for example, a kinetic mixing between the photon and the dark photon, and the mass for the dark photon. This model was, maybe you remember this, because this was proposed for the first time by Maxim, Josh, Joseph Pradler, and Alfredo Urbano. And is one of the few models that explain the ages anomaly together with the, one of the few like that is still alive, together with the one by Tomer, Diego, Nadav, and Ongwan. Yes, yes. Oh, that's above like few megaparsec, something like that, in order not to have problems. Right.
So this is something that's already constrained.
You're already constrained on dark. You mean also for dark matter explanation? Yes, exactly. You have exactly. So it's not something that you don't see, right? And then so you have to. Yeah. And that will be also important for us, and we can explain. We can avoid that because we will do everything at large redshift. Otherwise, you are really constrained. Okay. So this model is interesting because, so if you remember, the ages explanation for this was due to the fact that you could inject photons, okay, at much lower frequency. Okay. Why is so? So in this model, the axion-like particle is a dark matter. Okay. So what will happen is that the axion, through the usual coupling with dark photons this time, so be careful, will decay, right, producing dark photon. Sorry, say again? FF tilde is axion-like particle. Well, you can play also with dilaton, but we did this model. Actually, in general. Oh, yeah, sure, Race. Yes, sorry. Yeah, pseudoscalars. I am not doing the. You can play also with the dilaton, but actually in general, this is a simple model that Maxim and Josh thought about. But what I'm will explain to you, I think it can work in many different ways. For example, with Diego Redigo, we were also trying to see if this would be implemented with some splitting producing dark photon, and I will show you why, right? Because here, the main physics is the following. You have some dark matter candidate, in this case it's the axion, but maybe you have another candidate. It will produce some dark photons, in this case through simple decay, so it's a very simple kinematics, let's say, right? Then this dark photon can oscillate to photon, okay? So this dark photon will oscillate and produce photon via the kinetic mixing of the Lagrangian, okay? So in this case, actually, for the ages anomaly, for this anomaly, you don't couple direct with the axion to the photon, because otherwise stars like really kill you, right? So you have to go through adding also kinetic mixing in order to avoid also all the constraints, okay? So at this point, you can calculate, for example, as a first step, you can calculate how many dark photon you produce from the decay, okay? It's a very simple calculation. Today, at some frequency, there will be the decay rate, then this will be the axion mass, the frequency that you're observing today, and the Hubble scale at zeta star, where zeta star is defined by where the decay should happen in order to match to redshift to the right frequency bin, right? And if you see in a matter domination of all these scales, this scale is like omega to the 1/2. Okay. Remember that our goal was this one, omega to the 3/2, to the -3/2. Okay. So this should be something like this, and of course I'm missing a density of the dark matter. Okay. But these are dark photon. Okay. Then we need the dark photon to convert, and the dark photon. So at the end, you will have dn over d omega. This will be dn gamma prime omega d omega times the probability of conversion of this dark photon into photons. Okay. And this is the integral between 0 and z star of dz prime of this probability of conversion of gamma prime to gamma. Okay. And this probability of conversion goes like 1 over omega. Okay. Yes. What they call it mass, sorry. So this one is 1 over omega. Okay, so this is 1 over omega, this was omega 1/2. Okay, so we have reached 1 over omega to the half. Okay, so we are really not quite there because our goal was omega to the -3/2. Okay, but before like going to the last recipe that we came out with the other folks, let me also make a digression that I think is quite interesting for many other studies about all this term here. Okay, this term is how to compute the conversion of a dark photon to a photon or vice versa in our universe. Okay, until last year, so before the work that we did with Josh, Ongwan, and Sid, everything was done in an homogeneous universe. Okay, the idea is the following: you can have a resonant conversion because in a plasma the photon has a mass. Okay, as you know, of course, it's not a gravitational mass, right? It's just a gap in the dispersion relation. Okay, but if you write the plasma mass of the photon and gamma, this will be related. The square root you can relate to the number density of the electron in the medium, the mass over the electron, right? Typically, ions, everything. At the end of the day, here is like some forward Compton scattering, so will be suppressed by 1 over the mass of the particle. So typically, you care about the QED plasma and the electron that you're scattering off. Okay, and so to give you an idea of the numbers into the game, then this will be, for example, today in our universe, to 10 to the -14 electron volt, if you consider an average energy density of the electron. Okay, and then you can just redshift with the electron energy density. Okay, so if you do a plot, will be something like this. This is the redshift. This m gamma as a function of z. You will have something like this. So here, this stuff here is recombination around 10 to the 3. And this mass is around, let's say, 10 to the -9 electron volt. Okay. These spikes here, anyone knows what is this? This is reionization, exactly, where the number the free electron fraction Xe will change like rapidly, and this all will be around the redshift of 10. And so then today will be like 10 to the -14 electron volt or so. Okay. So why this is interesting? Because this is the mass, the effective mass of the photon in the plasma. So imagine that now you have in your model a dark photon with, let's say, a mass of 10 to the -10 electron volts. Yes, yes, go. Sure. No. Well, but these are no. Oh, if the light goes through the windows, it can be refracted without being absorbed. It's the same thing, right? You don't have to mess up the imaginary and the real part of the index of refraction. For sure, after recombination, the mean free path of the photon is huge, right? But it's just a forward Compton scattering is coherently enhanced, and then you have the index of refraction that you actually measure, for example, even for hydrogen. That's a good question. No. No. But it doesn't, it's not important that CMB is exactly. I mean, you just have a photon propagating into a plasma of electron, let's say, right? No, this is in the universe, right? So you will have like an electron density that, is this like, right? This is the electron density in the, you have electron in the universe, right? On large scale, that is what we are interested to at this scale of redshift. You have fluctuation, of course, that I will talk about at the megaparsec scale, but you can also consider like an homogeneous value, and you have electron, and so you have forward Compton scattering, you have coherent, and so you can compute, if you want, your like polarization tensors and calculate the plasma. Okay? Yes. No. I totally agree. Exactly. This is like what. Exactly. This is a very important point. Given the masses that you will be interested to, everything is happening at very large redshift, so it's really extragalactic interstellar medium. Okay, that's really important. But the point is that if you have, for example, a mass of 10 to the minus 10 electron volt, right? The important thing is that let's say that the dark photon mass is here, right? So you see at this point in redshift, you have a crossing between the two masses, right? This is very similar to what happened, for example, to matter effect for the neutrinos, right? When you have some resonant conversion, okay? So at this point in redshift, you will have a resonant conversion because the two mass match, okay? So the probability of conversion, for example, of even gamma to gamma prime, if you look, for example, at the CMB photon, but also vice versa, will be something like 2 pi. There will be the mixing square. There will be some typical scale to the -1. And then there is the variation as a function of time of the mass squared to the -1 evaluated at this point. Okay? And so this is the so-called Landau-Zinner approximation. Okay? And also for this approximation, it's also important what Mina was highlighting, that we are not dealing with galactic or very small scales. We are dealing here with very large fluctuation scales, okay, and not turbulent stuff. Because, for example, if you go, one of the things here, everything is homogeneous, okay? What we did actually was to say, look, the universe is not homogeneous, not even on large scale, right? Megaparsec scale. So the electron density that here I wrote as homogeneous will be oscillating, right? So also the plasma mass will be oscillating. So we'll do, especially at low redshift, will do something like this. Okay. And then you have to find a way in order to recompute this formula when you have all these multiple crossings. Okay. And we actually develop an analytical formalism using a mathematical theorem that is called the Rice Theorem, that was very well known in stochastic mathematics. Okay. That allows you just to recompute this formula, but averaging over the plasma oscillations. Okay. I don't have time. Yeah. I don't have time to explain the formalism. Maybe we can talk about this if you're interested in the discussion session, but it's a very cool formalism for which we really need cosmologists to provide us some input. Okay, but the take-home message is that you can compute this, and if you go on our pages, you can compute it in the inhomogeneous universe. Okay, and this will scale like one, as I say, like 1 over omega. Okay, yes. Yes, it is. No. The scales, at this redshift, for example, will be on megaparsec scales and will be well defined because you will have something well defined in a statistical sense, right? In the sense that, for example, imagine that you want to write the mass as a function of redshift, no? This will be something like 4 pi alpha over ma. Then there will be the electron density as a function of redshift. This will be the average electron density as a function of redshift plus a fluctuation in the number density of electrons. For most region of the universe apart reionization, this fluctuation is basically very similar to the baryon fluctuation. Okay, and the PDF, so the statistics of the baryon fluctuation is something that cosmologists will give us, right? It will be a Gaussian at large redshift, a log normal at low redshift, and then you can compute the fluctuation in the mass. Okay. Any further question before I move on about this stuff? Okay, and then the last part, the last few minutes, I will just explain the missing ingredient, because this goes like 1 over omega, this goes like omega to the 1/2, but there we are still missing an element. Okay, so yes. If the mass is not, what do you mean? Sorry, can you talk?
The mass of the photon is not fixed, but depends on the position. So the things that you show that oscillate a lot.
Right.
The resonant conversion is much smaller than the one that you compute.
No, it depends on the parameter space. It can be actually larger. So for example, yes. So let me show you something.
In different positions, the mass is different. So then you get a resonance.
No, you have to do
just for one point.
No, you have to average. No, this is like, for example, is a stochastic theorem, right? No, of course, like you don't for one point, but you don't know where, right? So, but the point is also, first of all,
I expect that is smaller.
The kinetic mix, of course, you don't have like, given that the kinetic mixing that we will look for will be small, right? It's not that you really are adding a lot of position, right? In the sense that it's already difficult to convert once. You're right? But the point is that you don't know where you are converting. It's a kind of an average between all the possibilities that you have to convert. Okay, let's say, for example, you fix a mass of the dark photon here, right? You see that you are actually crossing this line in many, many positions. So as you said, it's not that you convert in all these positions at the end of the day, because the kinetic mixing will be very small. And this is precisely what is difficult to compute, and what we computed like in a statistical sense with the statistical theorem. And then we also took some simulations. You simulate some with n-body kit, you take some log normal fields, and you just put through it photons going through. Okay, these different inhomogeneities. And actually the result of the n-body simulation is that in accordance also with our analytical estimate. And for some masses, actually the resonant emission is enhanced with respect to the homogeneous, and for some masses it instead is reduced. Okay, if you take, for example, let's say this mass here that maybe you cannot see, like in the homogeneous case, you would convert just at this redshift. Okay, if you instead have fluctuation, you can convert also later on.
I understand, but you don't know the matter power from below redshift 10 very well,
no? No, we cut, for example, we don't consider the reionization like between 6 and 20, because that is really where we don't know. Above 20, we know it very well. And below 6, we use n-body simulation by Eagle's collaboration, for example. And so we use their power spectrum. Okay. And the point is that even if you cut this line, there will be other resonance later on. If you look at this formula, you can easily convince yourself that the later it happens, the better it is. Look at the frequency omega, this red shifting. So the later the frequency will be the smaller, the probability will be larger. Yes. All these details we discuss in our couple paper of last year. Okay, very nice. I think that, okay, we'll conclude. We are also having a lot of discussion. I like this. And there is an extra ingredient that is missing, and it's actually Maxime, Alfred, and Josh were missing when they were thinking about the ages anomaly. And is the following. So typically, this decay, the decay rate will be something like this. Okay. However, if you have, let's say that you have a background of dark photon that you produce somehow, right, with in the dark sector, for example. Okay. Then when you compute your Boltzmann equation, which is a very simple Boltzmann equation because it's just a two-body decay. Okay, you will have stimulated emission. With this being the distribution of the dark photon of your background at the frequency that is half the mass of the axion. Okay, and this will actually bring you another 1 over omega in the region of the parameter space that we care about. Okay, So at the end of the day, you will have omega to the minus half here, omega to the minus 1 here. You get an omega to the minus 3 half, and we get a really beautiful fit to data. Basically, without the stimulated emission, Alfredo and Maxime were getting something like this to the minus half. With the stimulated emission, we are getting a perfect fit. And the parameter space that can explain it is not huge because you have many constraints. For example, you have constraint from CMB, right? Because like you have constraint, for example, can I take like a couple of minutes because we had like a lot of discussion. So let me write it here. Let me write just the constraints that we have in this model. So the goal was reached, right? Omega to the minus 3 half. This actually is the best fit. I mean, in terms of dark matter explanation, I think that our fit is the best one out there for the moment. There are a lot of constraints. For example, you have CMB constraint on the mass of gamma prime and the mixing, okay? Because in this case, we are converting dark photon into photon, okay? Yes, Mina. Yeah, it's very, to the dark photon is big. So like FA should be around 100 JeV. Yes, exactly. So you would need, we didn't carry out any model buildings. It's dark matter. Dark matter and the mass is like 10 to the minus 14 electron volt. 40, sorry, 4 electron. Sorry. Well, for the decay, for example, of the dark photon and not like back reaction, for example, or like producing too many dark photon and things like that, we actually have to work this one of the other, not constrained, but in order to carry on the computation, one is to be careful. Because, I mean, the model is similar also to the models by Pratik, for example, Agrawal, or like Raymond Ko, in which they were trying to produce dark photon, okay? But in that case, the mass were very similar. In this case, instead, we have the dark photon mass that is very small. So like the mass will be of this type. Let's say MA roughly 10 to the minus 4 electron volt, and gamma prime roughly 10 to the minus 13, 10 to the minus 14 electron volt. Okay, this will be the parameters. Yeah, on the dark photon, yes, good. This is another important constraint from N effective, for example. And the temperature of gamma prime should be at least like smaller than 0.2. The CMB temperature is actually safe even for future, unfortunately also for future surveys because everything is scaled like 2 to the 4th. Right, exactly. So the decay is actually one of the constraints also is coming also for like don't decay too much, for example. And for example, you have like CMB also bound, not just the lifetime of the universe, actually, even stronger than that. Because if you look at CMB bound on lifetime, they are a little bit stronger. So you cannot have much of dark matter decaying because otherwise you are changing basically the late integrated Sachs-Wolf effect. Okay. So, but with this coupling and this mass, even with the stimulated emission, you are fine. Right. Yes. Yeah, we can discuss, but this is like, I mean, the only thing that actually, I don't have here a plot also for the MCMC, you know, like for the exploration of the parameter space. But one of the main reasons in order that the parameter space will be small is also because you have to be in a region of all the parameters, right? For which, maybe this is what you are thinking about. For example, when you decay into this like dark photon, for example, you're producing a lot of them, okay? Then, for example, if you have, imagine that you have a thermal population of this dark photon, produce some dark sector, then you're also injecting with the decay of the axion a lot of non-thermal dark photon, okay? And it can mess up things. Mm-hmm. Well, you can. So I think actually you can even play with like some, this is actually what also Maxime was saying, like if you have some kind of also clockwork theory, right? You can also separate what you mean by, you know, the decay constant with also like all the other, for example, coupling to what you would define. Yeah, I mean, for the universe that we consider about, yes. Also because it's dark matter and this seems to be consistent. For all, then of course we didn't think about how you produce this. This I agree. No, this is like this is like this. I agree. This is something that we didn't investigate. Like it's phenomenological. We just like, you know, we take care of the fact that if you assume that this is dark matter, then you're not inconsistent with yourself or with astrophysics and cosmology, right? Because you know you may decay very fast, right? Well, I mean, I don't know. Like with this, it's not clear to me, right? Okay, we can talk about it later, but I mean, you know, like if the decay is so large, like FA is so large, yeah, we can think about this, but it's not something that we have been investigating. And the bound that we have is of like one that like also in exactly if FA is small. Sorry, I agree. Well,
Let's try to move on.
yeah, that's fine. That's fine. I like this. So I mean, I like this. So right, it's true. Always about axiom. With more normal decaying constant. And but yeah, I mean, so at the end of the day, like we didn't investigate the UV complete, you know, actually models like using some kind of clockwork in which you may separate like also the coupling with, you know, this kind of hypercharge and the QCD in the dark sector. Okay, but we didn't look at that. Also because this model was, you know, the first time was shown like a couple of years ago by Maxime, and I think that they didn't consider this either. But at the end of the day, the fit to arcade is very good, and actually within the same parameter space, we also think that we can explain also the ages anomaly. So it's possible that all this radio background that you have around in the universe may be due to this kind of model, and of course we'll be interested to, you know, to explore UV completion of this. So, you know, I think I'm done. So if you have any question, probably. Yeah, now I don't know because Josh is going to talk, but even after I will be happy to reply.